With this lecture, we start the second part of this course that deals with automata. And the first thing we will do, and that's the topic of this lecture, is we will discuss about the basic concepts of an alphabet, a word, and a language. Some of these concepts we have seen before as examples in the early part of this course. So I start with a basic definition. And the first thing I want to define is what is an alphabet. So I will call an alphabet, and typically in this course we will denote them by sigma. So an alphabet sigma is a finite set. And the elements of this finite set, they are called letters. So there you have the concept of letter and the concept of alphabet. They can also be called sometimes symbols. And then we have the notion of a word. So a word W over sigma is just simply a sequence of letters from sigma. So in other words, W is going to be just a sequence, say x1, x2, xm, for some m greater than or equal to 0, and with xi from sigma for all I between 1 and m. We also have the concept of an empty word. This we typically define by, typically denote by epsilon. It could also be denoted by lambda in some other textbooks. Sometimes it's also denoted by 1, but in this course we will typically stay with epsilon. So the empty word epsilon has no letters. So in other words, if you think that words are really finite sequences, so this is really the it is the empty sequence. And we are also going to denote by sigma star the set of all words over sigma. So in other words, sigma star is all these sequences of letters with m greater than or equal to 0, which includes the empty word, and xi, a letter from sigma, for all I between 1 and m. And I want to give you some examples. So, for example, we could have the alphabet sigma to be made of letters, say, A, B, and C, and words over sigma so we could have, for example, the empty word. We could have A is a word, it's a sequence formed by just one single letter. So is word B, so it's word C, but also it's word A, B, and also we could have A, C, B, B, C, A. For example, that's also a word from over sigma. Here is another possibility. Sigma is the binary alphabet, so it's made just of two letters, let's say 0 and 1. And words over sigma, in this case, you could have epsilon, the empty word. You could have word 1. You could also have word this one, and obviously much more than that. And I want to give you now another definition. I want to define the length of a word. So if I have a word W to be x1, x2, xm, for some m greater than or equal to 0, and with xi being letters. So for such a word, the length of W denoted by W between these vertical bars is M. So in other words, it's exactly the number of letters that you have in the word W. We also say that each letter xi occurs in W. And you might also want to count the number of occurrences. So the number of occurrences of some letter A from sigma in W is denoted like this. You have W in between vertical bars, and then we indicate by A, meaning that we are just counting how many A's do you have in word W. And here is some example. So if we have, for example, the empty word, the length of the empty word is obviously 0. It doesn't have any letters. But the length of word, say, A, B, B, C, C, is obviously 5. It consists of 5 letters. And if we denote this by W, just so that I have a shorter notation, so the number of A's in W is 1. A has only one single occurrence, and that's on this first position of W. But the number of occurrences of B in W is 2. We have 2 letter B's in W. And the number of occurrences of C in W, that's also 2. We have 2 occurrences of C. As a matter of fact, also as a matter of notation, this W, which was in our example A, B, B, C, C, this could also be written in a shorter way by just writing A, B squared, C squared. And what I mean by squared is that you have 2 consecutive occurrences of B followed by 2 consecutive occurrences of C. This is quite a handy notation when you have longer words. So here is another definition I want to introduce, and that's the concatenation of 2 words. So if I have 2 words, U, made up of letters, say, X1, XM, and I also have another word, V, made of letters Y1 all the way to YN. So we have M and N greater than or equal to 0, and we have XI in sigma for all i's from 1 to M, and we have YJ in sigma for all j's between 1 and N. So if I have 2 such words, the concatenation of U and V denoted U times V. But also sometimes we'll just write in short, we will just write UV. So we are omitting the dot between U and V. So this is defined to be simply all the letters making up word U. So I'm writing all these letters X1, X2, all the way to XM, followed then by all the letters making up V. So Y1, Y2, all the way to YN. And just as an observation, obviously, if you are concatenating the empty word with any other word, and you are concatenating the empty word either on the left or on the right, obviously that's going to leave your word unchanged. So here is one example for this notion. So if we have, say, word U to be A, B, B, C, C, and we have word V to be, say, B, A, C, then we have the concatenation UV is, first I'm writing all the letters of U, so that's A, B, B, C, C, and then followed by B, A, C, all the letters of V. So that's the word UV, the concatenation of U and V. And now I switch to the last set of definitions and examples that I wanted to give in this lecture. And simply I define the notion of a language. So a language L over alphabet sigma is simply a subset of sigma star. So in other words, a language is just a set of words over sigma. And it could be finite, it could be infinite, whatever it is in your example. So I give quickly an example. So the example could be if I have sigma to be a set of letters A, B, C. So for example, the empty set is a language. Is the empty language over sigma. And so is sigma star, that's the full language. All the words over sigma are in this language. But so is, for example, the set, say, AB, CBA, and ABA. That's also a language over sigma. But so is, for example, this set, which is made of all the words of the form AB to power N, C, A to power N, B for all N greater than or equal to, say, 5. That's also a language over sigma. Obviously, in this example, I'm also suggesting that languages could be defined inductively. So I just indicate some sort of structural rule for how the words in this language can be formed. So here is another example. If I had alphabet sigma to be A, B, I could also define the language L to be the set of words W, N, and greater than or equal to 0, where, for example, I define these words inductively in the following way. I say W0 is just made of one single letter, A, and then words WI1, I plus 1 is exactly WI concatenated with, say, B. And it can be proved by induction, but I will not do it here, but it can be proved by induction. Wn is exactly a b to power n for all n greater than or equal to 0. And finally, the last concept I have in this lecture is that of a factor, and as a special case, the notion of prefix and suffix. So I will say that if we have two words over sigma, so u and w are from sigma star, I'm going to say that u is a factor of w if simply u is somewhere inside u. So w is of the form x, u, y for some x and y in sigma star. So somewhere inside word w, you find the word u. In this case, you are going to say that u is a factor of w. And we also say that u is a prefix of w if w is of the form u, y for some y in sigma star. So in other words, it's a prefix if u is right here in the beginning of w. And then we say also that u is a suffix of w if w is of the form x, u for some x in sigma star. So the notion of a suffix is that u is right here at the end of w. And we also say that u is a proper, so that the stress is on word proper. So it's a proper factor. We also have the same concept for prefix or proper prefix, proper suffix. If u is a factor, and for the other concepts, u is a prefix, u is a suffix. And u is different than the empty word, and u is different than w. So it's a proper factor, prefix, suffix if it's not the empty word and it's not the full word, and it has the required property. So then we will call it a proper factor, prefix, or suffix. And just one more notation that in fact we have had in one of our exercises last week, and that's the mirror image. So if you have u to be the word, say, x1, x2, xm for some m greater than or equal to 0, and all these xi's letters from sigma. So mirror image of u is u r from reverse. So it's just the same letters but written right to left. So we start with letter xm and you end up with letters x2, x1.